All right. Hello, everyone, and welcome to this Stockholm Azure Meetup. My name is Gunnar Grosch, and I've been invited here today to talk to you about chaos engineering for serverless. But before we kick things off, I'd like to thank the sponsors we have tonight. You see them on screen right now. So thanks a lot to them. And this is streaming through YouTube, as you know. Please subscribe to the channel as well, so you'll get notified about new streams coming up. All right, so without further ado, let's jump into tonight's presentation. So the topic, as I said, is chaos engineering, and specifically for serverless within Azure. I've been doing these types of presentations for a while in regards to serverless for AWS. So it's going to be exciting to look at a bit at the same things, but for Azure instead. So this is kind of the gist of tonight's talk, that the principles of chaos engineering has been battle tested for years using traditional infrastructure and containerized microservices. But how do chaos engineering principles work with serverless functions and managed services? And this is the agenda. We have a lot to cover. We're going to start off with what chaos engineering is. And to begin with, this isn't going to be specifically focused on serverless. So even if you're not using serverless today, you'll get a great insight into chaos engineering and how that works. I'm going to try to keep an eye on the chat. So if you have any questions, just write them in the chat, and hopefully I'll be able to see them during the stream. Next up, we'll move into the motivations behind doing chaos engineering, why we do chaos engineering. Then we'll look at how to run chaos experiments before we move over to the serverless part of the presentation. And we'll look at basically what serverless is and how it works. And then we'll move over to looking at some of the challenges around using serverless. And in the end, hopefully we'll be able to do a few smaller chaos experiments in Azure as well. So let's jump into it straight away. Right. So shortly about me, I am an evangelist working at Opsio, based here in Sweden. My background is in development, operations, and management. So I've been working in IT for about 20 years now. I am an organizer of use groups and conferences, mainly focusing on AWS and serverless communities. I'm also helping out organizing the Serverless Days conference, both the Stockholm one and the global virtual Serverless Days conference. I've been named an AWS Serverless Hero, which I guess means that I've done something good around AWS and serverless. And lastly, but perhaps most important, I'm a father. I have 3 kids, so I know quite a lot about chaos, definitely. All right, so let's jump into it. What is chaos engineering? Chaos engineering is not about breaking things. We often hear about breaking things on purpose, and saying that it's great marketing lingo, and it helps draw attention to the practice of chaos engineering. But so there's nothing wrong with using that phrase, but we have to agree upon that breaking things isn't the purpose with chaos engineering. Casey Rosenthal, previously at Netflix, one of the creators of chaos engineering, famously said that, "I'm pretty sure that I won't have a job very long if I break things on purpose all day." And sure, we do break things now and then using chaos engineering, but the breaking part isn't the purpose. Learning is the purpose. And chaos engineering is not only for production. we often hear that chaos engineering should be used in production. And hearing this can be an obstacle for anyone trying to introduce chaos engineering in their organization. We want to do it as close to production as possible. But you can do experiments in test environments, in dev environments, in staging, and in playground environments, whatever you have available. But the more production-like, the better. The better the learning will be from your experiments. So if you're not able to do it in production, think about replaying traffic, using it together with load testing and so on, so that you're able to get a more production-like environment in doing the experiments in. And there are a bunch of major companies doing chaos engineering and doing chaos engineering successfully without doing it in production. And depending on what type of production environment they have, it might be an obstacle of doing it in production. So they're doing it in other types of environments instead. And another thing is that chaos engineering is not only for big streaming companies. When talking about chaos engineering, we have the Netflix reference used over and over again. And there are reasons why we do it. They have a head start as Netflix created chaos engineering. And they're also a company with big brand recognition. So it's easy to use them as an example. But you don't have to be Netflix to do chaos engineering. You don't even have to be like Netflix. And data shows that more and more companies are hiring chaos engineers or site reliability engineers with the responsibility to do chaos engineering. And chaos engineering is now used by companies ranging from big e-commerce companies to fintechs to banking, as well as smaller startups. As long as you're committed to being reliable, having a reliable service, chaos engineering is definitely a tool or a practice that can help. And you can't really have a chaos engineering presentation without showing this slide. Principlesofchaos.org is a website that was released alongside the book on chaos engineering, the first book of chaos engineering. So chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. And reading this shows that it's less about doing things that are chaotic and more about experimenting. So the chaos part of chaos engineering is more about what is inherent in the systems. So there is chaos in every system. And let's break that down a bit then. So chaos engineering is about performing controlled experiments to inject failures. And doing experiments makes it sound quite scientific. And to be honest, it is scientific. We create a control experiment and we measure the result. And some people compare it to a vaccine, which perhaps is a great comparison these days, in that we inject failure into a system to make it stronger. And chaos engineering is about finding the weaknesses in the system and fixing them before they break. So no matter how much we focus on making our systems resilient to failure, there are always unknown factors that come into play. That can be traffic patterns, it can be third-party dependencies, network issues, code deploys, configuration changes, and so on. So by doing our experiments and measuring the results, we can draw out weak points in the system. And finding the weak points and fixing these can help us avoid that big outage that we know never occur at the right time. And chaos engineering is about building confidence in your system, but also building confidence in your organization. So by building or finding weaknesses and doing these controlled experiments that I mentioned, we can build confidence in the system. We build confidence in how the system works. But we also build confidence in the organization. The people that manage and operate the system, they are key in a resilient system. So by building confidence, we gain trust. So perform chaos experiments and you will learn new things about your application. So let's Well, we've looked at what chaos engineering is. So let's look at some of the motivations behind why we want to do chaos experiments. Nines don't matter if users aren't happy. That's a famous quote by Charity Majors of Honeycomb. So we can have our dashboards that are full with SLAs, SLOs, SLIs, and whatnot. But what really matters is having happy users. So let's look at some of these motivations. Are your customers getting the experience they should from your system? Everyone who builds or runs a system has customers, be it internal customers or external customers. We often say that nothing is free on the internet. So no matter if you run an e-commerce site, an ad-driven blog, or some type of SaaS solution, downtime or issues probably cost you money. So it can be in decreased sales or just by users leaving your platform. So is downtime or issue costing you money? And what happens when the incident is there? Are you confident in that your monitoring and alerting will actually notice? Will the on-call get that page needed to start engaging with the incident? And is your organization ready to handle outages? You probably have your runbooks, your playbooks describing how to act in case of fire in your building. Or in case of outages in your application. But the question is your organization ready to handle these outages? Because even though we have these playbooks in place, we perhaps don't practice it the way we should. So are you doing your fire drills, but for incidents in your system? And are you learning from incidents? Every time there is an incident, there is a huge opportunity to learn. We learn about the conditions that exist for the incident to be able to take place. So what about learning from controlled incidents? We're able to do that by using chaos experiments and having these incidents, but in a controlled fashion. Hopefully you know Werner Vogels. He's the CTO of Amazon. He has this famous quote that says that everything fails all the time. And Werner should know, if you somehow were involved in some type of internet solution back in 2017, you were probably affected by the big S3 outage, Amazon's or Amazon Web Services object store. And that had a huge effect on the entire internet. So even though perhaps your own solution didn't have an incident, many used S3 as a third-party dependency. So they were affected, even though the outage was somewhere else by someone else. And this is just one example of something that can happen to someone else and can affect you. Last year, we had big configuration change made by Google, which affected a huge chunk of their services, Gmail, YouTube, Drive, and so on. But that also affected third parties like Vimeo and Snap and so on. Verizon, I remember, had a big routing issue last year as well, which affected a huge part of the internet as well, because traffic wasn't able to flow to different parts of the internet. Cloudflare did a big software deploy, which in turn caused CPU spikes within their infrastructure. And many people use Cloudflare without even knowing it today. So that was also something that affected a big part of the internet. So even though you have control of your own infrastructure, you might be affected by things that occur on the internet. And speaking of Netflix, well, even though Netflix do chaos engineering and they are successful at it, they have incidents as well every now and then. So just by using chaos engineering, you can still have incidents. It's just a matter of having them less often, perhaps. So that brings us to me, perhaps greatest motivation behind chaos engineering. Don't ask what happens if a system fails. Ask what happens when it fails. So we should remember that a resilient system isn't one that does not fail, but it's one that maintains an acceptable level of service in the face of failure. One that is able to adapt to these failures and still deliver good enough service to the users. So what happens when the system fails? Well, chaos engineering is able to help us reveal that. So we've seen now what chaos engineering is and some of the motivations why we want to do it. So let's look at how to run chaos experiments. And we'll do this by following some simple steps. We're going to define the steady state. We're going to form an hypothesis. We're going to plan and run our experiment. And then we're going to measure and learn, and then scale up and abort and fix. So let's jump into those. First off, the first step, define the steady state. And the steady state, that's more or less the normal behavior of a system over time. And that is how the system behaves, its ups and downs, but over time. And we can define this steady state by either using system metrics, and system metrics might be CPU, storage, number of instances running, and so on. But also business metrics, and business metrics might be number of purchases or number of active users and so on. And business metrics, they are usually more useful because thinking about having happy users, as Charity Major said, the users don't really care about how many instances we have or what the CPU levels are. They just want to have a working service. And the business metrics, they are often more a metric of how happy our users are. If we have, for instance, a metric over the number of purchases or items put into a cart, well, that probably means that we're able to see if the users are still using the service in the same way as they normally do in the steady state. And it's important to remember that steady state isn't necessarily continuous. The steady state can differ depending on the day of the week, month of the year, and so on. Think about Black Friday, for instance, in e-commerce and shopping. So look at the steady state, how it differs over time as well. Next up, we do step 2, which is forming our hypothesis. And an hypothesis, that is something that we use what ifs to find. So what if the database goes down? What if there is latency in our system? And so on. So we ask these what ifs to try to form an hypothesis that can help us then create an experiment around this. And doing these what ifs, well, that's a great way to just start thinking about how does the system work? How do we handle these things today already? And we should remember that chaos and the chaos experiments, they can be injected at any layer of the stack. So it might be on the infrastructure layer, for instance, by shutting down VMs or destroying pods. But it can also be on the application layer by creating exceptions in our code, or at the human level. What happens if Tom isn't at work today? He's usually the one that handles these types of issues. So when we're thinking about our what ifs, well, think about all types of incidents that could happen and ask those types of questions. And we're using the if-then method, which is the scientific way of creating an hypothesis. If the database goes down, then we will move to the fallback database, for instance. if Tom isn't at work today, then Paul will do his job instead. So use the if then to create this hypothesis. And when creating the hypothesis, we many times find things that we straight away figure out that it won't work. So doing these thought experiments is usually a good way of finding weaknesses in the system without even doing any experiments. So we find the known problems and fix those. If the primary database goes down, we don't have any fallback. Well, there's a problem to fix without even doing a chaos experiment. So now with our hypothesis formed, if the database goes down, we move to the fallback database. Then it's time to plan and run this experiment. And we start off easily by having a bunch of smart people in the room and whiteboarding the experiment in detail. We include the people that know about these parts of the system. We include people that are affected by this experiment. And we try to whiteboard the experiment in detail so we know, or at least try to know, what is going to happen when we run the experiment. And we think about the blast radius of our experiments. So creating the experiment usually means that we decide based on our hypothesis, how should this experiment work? And then we try to make it as small as possible to begin with, because we don't want to get an experiment or create an experiment that actually causes a big outage. Of course not. We want to do an experiment that proves our hypothesis. If the primary database goes down, we move to the fallback. And if we prove that hypothesis, well, we don't have a failure. But having a small blast radius means that we won't have a big outage, even though things might actually cause some sort of incident. And the blast radius can be set many different ways. It might be a subset of users only perform an experiment on Norwegian users, or only perform this experiment on one Azure function, not the entire stack of functions. So find ways to contain that blast radius with your experiments to make them small and controllable. And it's really important when doing chaos engineering that we involve people and we notify people what's going to happen. You don't want to be the person that has or creates an experiment, runs it, and you then actually cause some sort of incident. Be it that perhaps you're doing it in a test environment, but at the same time we have developers trying to perform tests. So make sure that people know what you're doing. Involving people is a good way to get acceptance and actually get people involved and get people to want to be involved in this process as well. Because to be honest, being a chaos engineer it's quite fun. And it's really important that we know how to abort our experiments. So have this stop button ready. No matter if you're doing an experiment where you're shutting down instances, or if you're doing an experiment where you are performing something around the database, you need to have a way to abort the experiment. Because otherwise you might run into problems. You might have users that are affected. So make sure that you have that abort route ready. All right, so now we've created our experiment and we've run our experiment. Now it's time to measure and to learn from the experiment. And the metrics we talked about earlier in regards to the steady state, those metrics will now be used to then prove or disprove the hypothesis. So if we, for instance, have metrics around number of purchases, well, while we're doing our experiment, did those metrics go down? Did users get affected by the experiment? Or if it's a matter of metrics around CPU or number of hosts and so on, we use these metrics to then prove or disprove the hypothesis. We took down the primary database. And we moved over to the fallback database, and users were still able to shop as usual. So the question is, was the system resilient to the injected failure? And that's a quite easy question to answer, because we have these metrics in place, and we're then able to see. And often when we build the systems today, or an application, they are built in a distributed way. So they are built with high availability and so on, so that they should be able to handle different types of failure. Using auto-scaling, using different techniques then to be able to handle that a virtual machine stops working, or that X number of containers isn't running, and so on. So this is a great way to check that resilience that we had at the architecture stage actually works. And a good question is to see, did anything unexpected happen? Because when we do our experiments, and we've whiteboarded the experiment in detail, we talk to a lot of people, very often we see things that we perhaps didn't know. There are unknowns within our system. And the more distributed a system is, the more unknowns there are. We can't really plan for everything around how a big system today works. So often we find unexpected things, but unexpected doesn't mean negative. It might be positive effects as well. We might have different ways of resilience or reliability, robustness, and so on in our system that we didn't think about. We didn't know that the system would behave in this way when this virtual machine was taken down, for instance. And then when we've done this experiment, once again, it's important to include people in this. So share the progress you've made and the success, because success, it's a word that I think is important, because no matter if our experiment means that we proved or disproved our hypothesis, success in this case is that we've actually done an experiment. We've learned something new, most likely. Be it that we found issues with the system, we found bugs in code, or we found issues with infrastructure. That's success as well, because that's something that we can fix and then make sure that doesn't happen the next time, or night time, where we usually have big outages. And the next step then is to move on with our experiments. And so we use the learnings, as I said, to improve our system. So we can fix these bugs, and we have our bug reports and infrastructure issues and so on to improve the system. And then with the confidence that we've gained in doing our experiment, we're able to scale up. So we can think about the blast radius that we set before. We only did this experiment on Norwegian users. Well, now we can scale up and include the entire Nordics, for instance. We can include Europe. We can include more virtual machines, or more Azure functions, and so on. So scale up the experiment and see what the effects are then. That's a repeat. So with this increased scope that we get when we're scaling up our experiment, we usually see new effects that we don't have on a smaller experiment. Because perhaps if we're only affecting 5% of users, that might not create this effect in the system that will cause an outage or an incident. But with 10% of users, or 15% of users, for instance, experiencing latency, well, that might cause issues in a different way. So doing these increases in scope is a great way to find new issues as well. All right, so now moving on from the chaos engineering part, let's move on over to the serverless part of this presentation. So in short, I want to start with what serverless is. most of you are probably familiar with serverless today, but let's just do a quick recap on what serverless is. So this is the Microsoft definition of serverless, and it states that serverless computing enables developers to build applications faster by eliminating the need for them to manage infrastructure. And eliminating the need for them to manage infrastructure isn't so much about the actual infrastructure as it is about what running infrastructure means. It's about letting someone else do the long time work that is involved with running servers and databases and so on. And it lets you focus on maximum business value. And serverless today is not only about functions as a service like Azure Functions, but the serverless landscape today consists of a bunch of services, both in Azure, in AWS, Google Cloud, and so on. So there is no need to provision or maintain any servers. We don't have any server management. And there's no software for us to install, any runtimes to maintain or administer. We can have automatically scaled applications. They can scale from 0 to the highest peaks, or they can scale by us adjusting the capacity units rather than the number of individual servers as we probably used to do. And with serverless, we pay for value, as we say. We pay for a consistent throughput or an execution duration rather than, once again, the number of servers. And serverless provides built-in availability and fault tolerance. So you, as an architect or a designer, you don't have to architect for these capabilities on the service level, since the services running the application provides this high availability and fault tolerance by default. But that's important to remember, that this is at a service level. You still build an architecture where you tie different services together. And how you do those, well, that's how you build a fault-tolerant, robust, and reliable application. So this brings us to some of the challenges around serverless as well. And if you now think that, well, are there challenges with serverless? I think that's good, because then perhaps you might leave this session with some new things to think about when doing serverless applications. Serverless computing enables developers to build applications faster by eliminating the need for them to manage infrastructure. And that's that Azure Microsoft definition once again. And I think that's great that we don't have to think and manage about the infrastructure. But if you ever talk serverless to someone, an old server hugger, you've probably heard this line, that there are still servers in serverless. And there are. The thing is just that we don't manage them. And this leads us to some of the challenges then. So we don't have any servers to manage, which is good. But that also means that we have potential sources of failure that we don't or can't control. So the failure modes for the underlying infrastructure is quite unknown. I'm all for less infrastructure work. I'm all for doing less and less heavy lifting. But we have to remember that every time someone sets up or configures infrastructure, they usually learn a lot about how that infrastructure works. The people setting it up or maintaining it, they find sources of failure and are aware of them. And once again, in serverless, in fully managed services, things are unknown for us in many ways. And besides Azure Functions, as I mentioned before, as the perhaps most common part of our serverless applications, there are lots and lots of different services to choose from. Cosmos DB, and so on. And having all of these services, everyone with its own potential sources of failure, everyone with its own unknown failure modes, is, of course, a system that has more more built-in unknown failure modes for us. And each of these functions, Azure functions, and each of these services that we're using in our architecture, they all have their specific configuration. They all have their specific security policies. And this is, of course, great for control. But to be honest, it also gives us the opportunity to introduce failure as well, by doing misconfigurations or by setting the incorrect security policies. And the architectures that we build with serverless, they are usually a lot more granular in that they contain so many different functions, services, and interconnections. So all in all, with serverless, we usually say that we have more inherent chaos because the systems, the serverless applications that we build, they are distributed systems by default. And chaos engineering, to me, is a perfect fit for serverless. And I like to use quotes, but if you can't get anyone else to say it, you just have to quote yourself. But what I mean by this is that serverless, with its inherent chaos and with its granular architectures, is well suited for chaos engineering. Because, as I said, using chaos experiments, it can help us build more reliable and resilient applications by finding weaknesses, by testing how our application behave in the face of failure. And basically, to get started, we don't need anything more than the Azure CLI to start doing our easiest experiments. So now let's move over to some serverless chaos experiments. And I had a quote before, but don't quote me on this, but creating chaos experiments for traditional infrastructure, it can be fairly easy. You can shut down instances, you can destroy pods or containers, you can cripple network traffic and so on. Because even though they are managed services, we usually have control of a lot of the infrastructure with those more traditional infrastructure. So designing chaos experiments for serverless, it is a bit trickier, but it allows us to be creative and working with development and building systems. It's probably what we do on a day-to-day basis is probably a lot harder anyway than building these experiments. All right. So creating experiments, we can usually start by looking at some of the common serverless weaknesses that we see in architectures today. And one is error handling. Are we handling errors in our applications correctly? So no matter if the error handling is inside our code or a feature in the service, we better make sure that we're handling errors correctly. And the cloud providers are doing releases that are taking some of this load away from us. But even though that's perhaps part of the service today, some part of the error handling, I, for one, want to test to make sure that it works. And that can be done by doing chaos experiments. And using Azure functions, different sort of dependencies, be it other Azure services or third parties, we need to and want to get our timeout values right. So how the timeout values are set so that they are properly configured. And in most cases, they are when we're inside that steady state. But when there are issues, be it with the platform or with something else on the internet, say we add latency, how does our timeout values work then? And today, more and more applications are built around event-driven architectures. And how we handle events is key, of course, then in these architectures. So are we queuing events correctly? What happens to our events if we have service failures and so on? And using many services and third-party dependencies means that we trust them to be there. But what happens if a service isn't there? Do we have fallbacks in place? Do we use graceful degradation and so on? That's also something we can use then to build our chaos experiments. And failovers. Well, I don't want to jinx us, but regional outages rarely happens, no matter if it's Azure, AWS, or Google Cloud. But having regional failover or multi-region is of course not only for entire regions having outages. It might be because you want to come or be closer to your users. And what happens if a major ISP has issues affecting traffic to that specific region? So having failover in place and knowing that it works as intended is something that we can work with. And these are some potential weaknesses that we see. And there are, of course, a lot of others as well. All right. So let's look at some practical serverless chaos experiments we can do. A word of caution, the architecture diagram is AWS here, but I'm going to try to translate it into Azure lingo. So sorry about that. So the simple architecture in this case is a web service. It has an API, a couple of functions that could be Azure functions instead, then an object store and a database, Cosmos DB, for instance. So we can then create experiments in this type of serverless environment. We can, for instance, inject errors into our code to see how the code handles these errors, or the function service handles these errors. We can create errors, we can create exceptions, and so on. We can, of course, remove downstream services. And this is one that I like to do when building solutions, because checking to see how does my application handle that a downstream service isn't available. And we can work with the concurrency of functions to see how it scales, or if it's limited, what happens if it doesn't scale as our architecture perhaps intended it to. And we can restrict the capacity of our databases as well to see. That could be to simulate a service issue with the database, or it can be to simulate a configuration error as well that might get introduced when doing deployments and so on. So we can work with our security policies, how we set security on different services, and introduce these errors to see how does our application behave if, for instance, clients aren't able to retrieve objects from a specific service. CORS is something that we tend to work with as well. Configuring CORS can always be a hassle, and introduce CORS configuration errors. Different type of service configuration errors, of course. And our functions have some sort of disk space that we sometimes use. It can be used for caching purposes. It might be used for transformation of data, images, and so on. And we rely on that disk space being there. But what happens if that disk space gets filled? That might be because we're using it incorrectly. It might be that data is larger than intended, and so on. So by filling disk on purpose, we're able to test how does our application behave in those cases. And then we move on to our, perhaps the mother of all chaos experiments for serverless, and that's latency. Latency is something that everyone that's worked with functions has probably been affected by latency sometime. That might be as cold starts, for instance. First time we run a function in a while, we might have cold start issues, but it can also be cloud provider issues. It can be runtime or code issues that we have in our application. It can be integration issues that we have latency caused by a third party, for instance. And of course, we can use latency to try and test our timeout values. And latency is perhaps one of the most common experiments that we're doing as well, because that's something that definitely can have a big effect on our application. And knowing how the application behaves when adding latency is definitely of value for us. So looking at these experiments that I've talked about now, there are some chaos engineering tools that can help us to perform experiments. First off, there's a company called Gremlin. Gremlin is perhaps today mainly focused on instances and containers in Kubernetes, but they have a part of their system that's called ALFI, Application Layer Fault Injection. And that can be used together with functions as well. The support is still quite limited, but they're working on newer implementations for it as well. And what's cool about Gremlin is that it's a SaaS tool. So they have an entire platform where you're building your experiments and then measuring the results of the experiments as well. There is the open source Chaos Toolkit. So that's an open source tool that can be used to create experiments. And this is built around, let's call it plugins that are created for a different type of services and solutions. And if something is missing for a specific service, you're able to create your own plugins as well. And so Chaos Toolkit is definitely a cool way of doing chaos experiments, but it can be a bit tricky to get started with. Then there's this observability tool called Thundra. Thundra, they are a traditional observability tool for serverless, but they've added a part in their tool that allows you to inject failure into your application. So you can test how, for instance, if you get an error in your application, and you'll directly see the results within the observability tool as well. So that's pretty sweet. And then we have my little open source tool, which is called Failure-azurefunctions. It's a Node.js library that can be used alongside or with your Azure functions. And it has two siblings with Failure Lambda and Failure Cloud functions as well. And this is a tool that I've created out of the needs that we saw around serverless chaos engineering. So looking at that, it's an NPM package for Node.js functions. It's available on GitHub and NPM, of course. And that text is quite small, but basically what you do is you install the package, and then you wrap your function handler with this tool. So you wrap it, and then you're able to add experiments through that. And the configuration is done using Azure Vault. So we're storing JSON object in Azure Vault, which contains all of our configuration, if it's enabled or not, and so on. And we have a few different failure modes to choose from. One is latency, so we're able to add latency to our functions. Another one is status code, which means that when we're perhaps we have an API, for instance, and instead of returning a 200 response, we can then inject failure and return a 404, 502, and so on. as a way to see how our application behaves, test our client applications, for instance, a front end, and so on. We can make the function throw an exception by adding that. And we can fill up disk space, as I mentioned before. And we have a deny list, so we're able to block requests to other services, be it other, in this case, Azure services or third-party requests as well. So this is perhaps an easy way of getting started doing chaos engineering for Azure functions. So before we wrap things up, let's look at a small chaos experiment. And we're going to do this by using a small application that I've built. This is a web app, and it's fairly easy. It's a simple web application. Once again, this shows an AWS architecture, but it's built with Azure services this time. So it's a static web page, and behind and that static web page, if I can go back here, it has 3 different functions that it's calling every 5 seconds, and for each time that function fetches data from Cosmos DB, and that data is then returned to the client, and what it returns is a URL for a new image to load, and then it loads that new image, and the client should hopefully get a new image every 5 seconds. And as the architecture diagram shows, it has 3 different functions, so that we're, in this case, able to test one by one to see or inject failure to them. So let's do the what if thing to create our hypothesis. What if my function takes an extra 400 milliseconds for each invocation? What if my function returns an error code? What if I can't get data from Cosmos DB? And then the hypothesis based on this is, if we inject failure to functions, then my application will use graceful degradation so that users won't notice these issues. All right. And with that, I'm going to move over to the demo. Let's see if we can get this working. There we go. Go on again. There we go. All right. So this is the web app, and right now it's loading as it should. Then let me show you. Just a second. Need to get Azure Vault up and running. There we go. All right. So I'm gonna do this. Try to do this using the CLI. Go. All right. And as I mentioned, this is an item that we're storing within Azure Vault that contains the configuration. Basically what we're doing to change the configuration is to update this item in Azure Vault. And I'm going to do a bit of copy pasting. Just a second. There we go. I hope That's visible. So this is using the Azure CLI. We can, of course, do it using the UI as well, but I think that's it takes a bit longer to do it that way, so I prefer to use the CLI. So this is just a second. What we're doing is we're creating a secret, or setting a secret that is related to function 1 in this case. And as you can see, the values here in this case is enabled false, which means that we are not performing an experiment at this time. So I'm going to change that value. I should have done that before I pasted. Just all right. Set that to true. Then the failure mode in this case is set to latency. That means that we will inject latency to our function. Let's increase that a bit. 400, 800. Like that. So we're able to set a minimum latency and a maximum latency. And that means that it will use something in between those numbers, so that we don't get a fixed latency each time, because that as well is something that perhaps wouldn't happen in reality. Instead, we would get latency that is moving up and down. We also have a value here that says rate, and right now it's set to 1. That means that if the rate is set to 1, we will inject this error on this failure on every invocation of the function. We could set it to 0.5. That means that it would inject failure in about half of the invocations instead, which also is something that perhaps might be more realistic instead of having the same issue happen all the time. So let me then hopefully, all right, it's created, looks good. And now looking at function 1, comparing to the other ones, we can see that it takes a whole lot longer for each invocation. There might be outliers based on my internet connectivity as well, but as you can see, it's 700 milliseconds compared to 200 on the other ones, 900 now, and so on. So what we're doing right now is injecting latency on all of these invocations. But as you can see, it's still working. If we were to add even more latency, perhaps based on timeout values, the function would time out instead, which is also something we can check for. And what I'd probably use this for is to check, for instance, with our front-end team, that how do you handle if a response from an API is above a certain time? Well, should we still wait for the result, or should we do something else in the meantime? All right, so that was function 1. Let's now try function 2 instead. Okay. And with function 2, we're gonna try something else. Same, it's a different one in Key Vault. Is enabled true, but instead of latency, I'm gonna change this to status code. Go, and the status code that I have right now is, there we go. The status code setting is set to 404. And what that would mean is that when we enable this, instead of returning a 200 response as we're getting right now, when we're calling the API, we're going to get a 404, not found instead. What we also can do is change the rate. So that instead of getting this on every invocation, we can get this on about half of the invocations, in this case, 0.5. Function 2 is enabled true, status code, and 0.5. That looks about right. Okay. There we go. Right now we can see that this time when it called, we got a status 404 instead of a 200. But since this is set to rate 0.5, yeah, right now we can see that the next one is status 200, then a 404, and so on. And this allows us to test, once again, how does the calling part of our application, in this case, the front end, the client, how does that handle these types of errors? Well, in this case, we can see that the front end doesn't handle the error. It just shows the error and doesn't reload any images. So that's perhaps a way of finding how should we handle a 404 or a 502 or whatever error we're throwing at the front end and the client. All right. And then finally, function number 3. Let's do that one as well. And in this case, I want to show off how we can use the deny list. So we can deny requests to specific URLs. So now change it to function number 3. Value is set to enabled. Let's change the rate back to 1. And the deny list is the last part here. As you can see right now, it says stars.documents.azure.com, and that should then include the calls for Cosmos DB. And this is a list, so we can add additional ones as well and have more than one call. So just check. And there we go. And that is updated. All right. And straight away, we can see that function number 3 is now getting a 502 error, which means that the function is trying to call Cosmos DB, but isn't really getting through. So instead, it's throwing a 502 error. And this, of course, is something that we can use to, as I said before, to check how our application behaves when a downstream service or a third-party dependency and so on isn't available for us. And these things happen, so it's definitely something that we should test for. And testing for it in traditional ways with our integrations tests and so on, it might show us some things, but doing it in the actual environment and doing it the way that users would see the issues probably shows us even more. All right, so that was 3 examples of how we can do chaos experiments. Let's jump back into the presentation. There we go. So with that, I want to just brief recap that I think it's important to remember that everything fails all the time, as Werner Vogel says. We do have failures in systems all the time, and that's really important to remember. And serverless in itself, it doesn't make your application resilient. Serverless services, they can be resilient, they can be reliable, robust, and so on. But it's a matter of how we stitch these different services together that matter in regards to building reliable applications. And chaos engineering, as I have said many times, it helps us find weaknesses in the system, and then we're able to fix those before they actually cause an outage. And chaos engineering is a lot about building confidence, so that we know how the system behaves in the face of failure. if we're able to build an experiment and try and test the system in reality, well, then we probably know a lot more about how it behaves in the face of failure. And I think it's easy, or it's important to remember that chaos engineering isn't rocket science. It's quite easy to get started with. You don't have to have full-time chaos engineers doing chaos experiments. You don't have to be Netflix. You don't have to have everything else in place. You can start small, do simple experiments to try your applications and test how it works. So I really suggest that you consider implementing chaos engineering in your organization. And if you want more around chaos engineering, there's a bunch of links. You should definitely follow Serverless Chaos on Twitter. It's a bot that retweets a lot of good information around chaos engineering. There's a few repos, of course, some labs, and a bunch of YouTube videos as well. We can probably add these somewhere later on. And with that, I would like to thank you, but let's check if there are any questions. I don't think we have any questions. No. So with that, I'll stick around in the chat. So if you have any questions, just post them there. Otherwise, feel free to DM me on LinkedIn at Gunnar Grosch, or connect on this is Twitter. DM me on Twitter or connect on LinkedIn. I'd be happy to answer any questions you have, or help you get started with chaos engineering and so on as well. All right, so we have questions. I got a message now. All right, so let's see. Is the session recorded? Yes, it is. What happens when you pose an irrelevant hypothesis? Well, if the hypothesis is irrelevant, I'm not sure exactly how it should be irrelevant. It should, of course, be something around your application, and as long as it is around that, I'd say that it is relevant. But you by irrelevant mean that a question or an hypothesis that isn't based around something that actually fails, well, then I guess you just prove the hypothesis. So you can either prove or disprove the hypothesis. If the question was around something else, please just add it again. All right, there was actually an explanation. When you realize that your metrics in the penultimate step are something very different from what you thought, and you need to rethink your hypothesis. I'd say that it's perhaps not uncommon that when you actually get to the stage that you do your experiments, you notice that there are things that you don't have metrics around, things that might be affected by your experiment. Then I think that is quite common. There's always the risk of having too many metrics, whatever the system is, having too many dashboards and so on. And so I think it's important to find the ones that matter to you, the ones that are important for your customers. And about rethinking the hypothesis, sure, that's definitely something that you can and should do if you realize that this is not something that you should create an experiment around or can create an experiment around. The steps that I showed before, perhaps you don't always move through them 1 through 5. You might go back and forth a bit between creating the hypothesis and defining the steady state and so on. Perhaps after you've created the experiment, you might notice that there are additional metrics that you need. In your own view, what is the difference between AWS metrics and Azure metrics? How can user groups benefit from each other in terms of chaos engineering? I'm not sure that I get that question. So if you're able to expand on that, I think that would be helpful. All right, we can get back to that afterwards. I'll stick around in the chat. So once again, thank you all very much for watching this session, and thanks to the organizers of Azure Stockholm Meetup for having me. It was great talking about Azure this time. And all right, thank you all very much.